over the topic rotational kinematics. This is an important topic under motion in a cycle. This is the study of how objects rotate and how they spin, determining their spinning speed and how far do they turn over time. Okay, it's not so much different from linear motion, but that in linear motion you saw that we're determining mostly how things were moving in a straight line. Now, in rotational kinematics, we describe the motion of objects that rotate around an axis. Okay, so in this topic, we'll explore key concepts like angular momentum. These are the key concepts that we'll have to master. Angular velocity, things like angular displacement. So these are the new terms that we'll have to master under this topic. Okay, angular acceleration. So you have to find a way to familiarize yourself with these key terms. Okay, so you will learn how do these quantities relate about rotating systems like wheels, gears, fans, and engines. Okay, so let's move on. Okay, suppose you have an object that is moving along a circle of radius r. I'll just draw something like this, whereby this is my y-axis, this is my x-axis. So if an object is moving along a circle of radius r, we realize that the radius itself, it won't change. What will be changing is the angle that is referred to as the rotational coordinate, theta. Okay, so we know that from mathematics, the distance along an arc is given by letter S. Okay, so the relationship between these three quantities is given by theta, which is equals to S over R. Okay, so this is an important relationship in rotational kinematics. Okay, so one thing that you have to know is that suppose that an object travels a full rotation. So our angle theta will be given by 2 pi. Okay, that's one thing that you have to always know. If I say 2 full rotations, it means I'm gonna have to say 2 pi multiplied by 2, which will be 4 pi. So a full rotation is denoted by 2 pi. Okay, in degrees, that's the radians actually. So in degrees, that will be 360 degrees. Okay, so let's move on to talk about something important once again in this topic, that is called average rotational velocity. Average rotational velocity. Okay, that is given by the letter W theta. Okay, so this quantity is equal to the change in rotational coordinate divided by the time interval during in which this change takes place. Okay, so we denoted here that this is our rotational coordinate theta. Okay, so one thing to know is that uh, our theta here, suppose an object moves from a certain position, maybe call it um, theta initial, suppose it was here, okay, at this position, say theta initial, and then maybe travels all the way up until around there, which I can call theta final. Okay, so our change in rotational coordinate will be given by theta final minus theta initial. Okay, so this is our change in rotational coordinate, in which we have to understand this thing because we are going to use it to calculate the average rotational velocity. So our average rotational velocity will be given by uh, change in rotational coordinate divided by change in time. Okay, so the SI unit for this average rotational velocity is S power of negative 1, right? This is the SI unit that we're using. Okay, so the subscript theta is here to remind you that the average rotational velocity is a signed quantity that can be positive or negative depending on the choice of positive direction of rotation for theta. Okay, so in this case, if we choose to move anti-clockwise, our theta will be positive. But suppose we choose to move in a clockwise direction, our theta will be, it will be negative. Okay, so let's move on to do a very simple question under this topic, okay, that you can find on Eric Mazar textbook. It says a car's engine is turning the crank is turning the crankshaft at 6,000 revolution per minute. Okay, the question asks what is the rotational speed? What is the rotational speed v? Okay, you're free to pause this video and try this question on your own. Okay, so to find the rotational speed v in terms of angular velocity, right, we can start by analyzing our question. We have rotational speed. We have our rotational speed that they give us is 6,000 revolution per minute. Okay, so one thing that you know is that a minute is not our standard unit that we usually use for our time. So we want to convert to seconds so that we remain with something with our preferable units. So 6,000 revolution uh, per minute. Okay, you can multiply and say 1 minute. I know that 1 minute is 60 seconds. So I will get 100 revolution per second. Now I know that I have my standard units over there. Okay, so now we can continue. What I know is that one revolution, as I explained in the diagram above, Okay, one revolution is equals to 2 pi radians. Okay, so now what I know is that I have 100,000 revolution per second. Okay, so if I multiply my 100 revolution per second by 2 pi, in which 2 pi is just in radians per revolution. Okay, 2 pi is one revolution, and then 100 seconds, 100 revolution per second, it is going to give me 200 pi radians per second. Okay, as I've said above, that the SI unit for average velocity is given by s power of negative 1, which is per second. And as you can see here, this is our units that we have. You can ignore these radians here and just write 200 pi per second. Okay, so this is our answer for this question. Okay, let's move on to another practice question under this topic. Okay, it's just a simple question which says, what is the rotational speed of a watch's second hand? Okay, it's our hand specifically. It's our hand. Okay, so to find the rotational speed of a watch's hands, we have to express the answer in radians per second, right? So we know also that one full resolution of a watch, okay, if you have your watch over here, starting here, so if you move all the way here up until here, this will move all the way here. So this is one revolution, okay, which is 60 seconds. Okay, so one full revolution is equals to 60 seconds. Okay, so in our own interpretation in terms of rotational coordinate, we know that one full revolution is equals to what? 2 pi radians. Okay, so we can go ahead now and calculate our rotational speed that we know is given by the formula that I defined above. Okay, so in this case, we start at theta equals to 0. We start at theta equals to 0 up until theta is equals to 2 pi. Okay, so our change in rotational coordinate divided by our change in time is going to be equal to 2 pi divided by our time, which is 60 seconds. So this is going to give us over pi over 30 radians per second. You can just choose to write pi over 30 per second. Okay, so here we calculated our speed, our rotational speed, but this is for a minute hand, the longer one. We have another one, a shorter one, for an hour hand. Okay, so we are not done. Okay, This was for a 1 hour hand. I mean, this was for a second hand, which is a minute hand. This was for a second hand. Okay. So now let's proceed and calculate the one for our hand now. Our hand. As required by the question, right? It says, what is the rotational speed of a watch's second hand? Of a watch's second hand. So this one is for a second hand. Now we have to go, we have found the first part of the answer. Now we have to find the one for the hour hand. Okay. So for the hour hand, we know that one full revolution is equals to, okay, this revolution is actually in 12 hours. Okay, is in 12 hours because the hour hand is going to travel all the way from 1, 2, 3, 3, 4 up until 12 when it is at this point. Okay, suppose it started from 0 over there up until it comes back again, that will be 12 hours. Okay, so we have to convert our hours to seconds. It's going to be 12 multiplied by 3.6, which is going to give us 43,200 seconds. Okay, 43,200 seconds. So now we can calculate again using the same formula, but now we're calculating the rotational speed for our hour hand, which is given by, okay, one full revolution is what? 2 pi once again, divided by our changing time, which is 43,200 seconds. Okay, so I'm going to get my answer is 1.5 times 10 power of -4 per second. So this is our answer.